Today we're going to talk about the chain rule. The chain rule is the kind of overarching mother of all derivative identities as to the way that you take a derivative. The very general way that you look at this would be that, if you have a function that is made up of another function that has an inside function of its own. So we have f of x equals g of h of x. So we have some composite function here where we have a function inside of another. This rule helps us to find the true derivative of this of f of x. Because it not only is going to respect g, but it's also going to respect h. And it works in this following method. The derivative of f of x is going to be the derivative of g of h of x multiplied by the derivative of h of x. So what's really happening here is that you apply the derivative of this main function, the whole thing, and you keep the inside function, this h of x, intact inside of it to start. You don't do anything with this inside function at all. You just kind of just take the derivative of g like you would with the power rule or product or quotient or any of those things. But then, because h of x exists inside of g, like it's inside of it already, that you have to account for that on the end. And that's where that's where the chain rule really shows its usefulness, in that you just kind of tack it on the end. But you always have to consider these inside functions. Now, since we have so far just discussed using the product rule, and the power rule, the product rule, and the quotient rule, we've only seen the inside function being just a simple x. Well, when this inside function is just a simple x, the derivative of x is 1, and anytime you multiply anything by 1, it stays the same, so it's kind of redundant. You don't write that 1 there. Well, if the inside function is something other than 1, you have to account for that. And so I'd like to show you a couple examples of how this exactly works. And it becomes very complicated down the line, and there are many examples, and most of your problems you will deal with from now on are going to have this inside function, but I just want to show you how it exactly works. So we're going to move on to this next slide here. If I were to ask you to take the derivative of a function like x squared, okay? Well, that's pretty simple. You are just going to apply the power rule to that. That's going to equal 2x. Simple enough, right? Well, what if I asked you to take the derivative of 2x squared? Well, you could immediately think of that in a different way. You could rewrite that like I've kind of taught you before. You could say, okay, well, get rid of the brackets. That's really simple. 2x squared, you have to square the 2 and square the x. So you end up with a 4x squared. Okay, so you see how that works? Well, this derivative just becomes 8x. Okay, well, we see how this becomes a little bit different right off the bat. Well, if I were, in this next example over here, to say, what if I looked at this in a slightly different way, which is in terms of the chain rule, okay? Well, the chain rule is going to say to look at this as two functions. An inside function, which is 2x, right? We see this inside part. I like to call it kind of the intimate operators on x, the things that are closest to x. The thing that is closest to x in this case is the 2. It's being multiplied by 2, and it's inside brackets, so it's that kind of like inside closed doors, for lack of a better expression. But then this 2x has the square operating on both the 2 and the x. Okay, so you're squaring something, but that something is not just an x anymore, it's a 2x. This is now a chain rule problem. I can look at it as a chain rule problem. So what I'm going to do here is I'm going to apply the power rule just like I would normally. Okay? I'm going to carry this 2 down. I'm going to take 1 away from it. But now, instead of just leaving it as it is, I have to apply the derivative of this inside function, which is now 2x, which the derivative of the inside function is 2. Okay? So let me carry you through this. So we start off, when we do this derivative, again, we carry the 2 down. So we have a 2. We then multiply our regular function, which is 2x, and we lower its exponent by 1. So 2 minus 1 becomes a 1. Okay? So it's just like the power rule. But then we have to multiply by the derivative of the inside function. And I'm going to zoom back for just a second. That's where this part comes in, okay? So what we've done so far is we have done the power rule, which, again, we pulled down the 2. We then took 1 away from the exponent, but we never changed the inside function. That h of x part, that 2x that we had before, is still there. We don't deal with that until the very end, which is this part right here. We deal with the derivative of it at the end. We tack it on at the end. And so, what's the derivative of 2x? It's 2. Yeah, I gave you a little bit of time for that. So we multiply by 2. Well, when we simplify this, we get 2 times 2 times 2, which is 8. And then we have an x, which is just x. So we see that these two answers match. Well, that's not a surprise, okay? All these rules of math that we know, breaking apart the brackets over here to create this simpler term, we were able to do our power rule and it works great. But the chain rule also works just as well, and it's way more useful in many other problems than this. But you can see that as long as we respect this inside portion of our function, as long as we can identify that there is a function inside of another function, then we can go ahead and use this chain rule to sometimes make things a lot simpler for us. And most times in the rest of this class, it is critical to think this way because there's no other way to solve a problem. So when we look back, it is mainly important to not only identify that you have a main function g, but that g in itself has a inside function h of x, so something other than x. And in reality, you can even think of this as having an x because the derivative of x is just 1, like I said before. But if the inside function is anything other than x, you're going to end up with this extra little bit that changes everything in your problem.